Alright, let's review this problem from the last time we met. Okay? We said we're trying to find solutions of this. We tried to factor it by grouping, but it wouldn't work. So we said factors of P divided by factors of Q. Remember that? Okay? So we said plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20, divided by factors of the first, which is plus or minus 1. And we said that even though that's still 12 things to try, it's way better than an infinite number of things to try, right? And so someone suggested, I said, where do you want to start? Someone suggested we use 4. Remember this? I know it's been a long time, but 1, -8, 11, and 20. We did use synthetic division, hoping that we were going to get a 0 for our remainder, right? So 1, 4, -4, -16, -5, -20, and miraculously we got a 0 for our remainder. Okay? Once we get one of our factors, we can take our remainder, which was 0, and we can write what we have left right here back into polynomial. Remember that? X squared minus 4x minus 5. And we can say to ourselves, self, can I factor this? And then I'm like, uh-huh. So those are the factors of that. So when we go to write all of our factors of our original problem, we have those those 2 that we just found from factoring our trinomial, plus we have the one that we know that worked from the beginning. Okay? So these are called what? Factors. And then what do we need to do to actually solve this equation? Set each of these factors equal to 0. So if I say x minus 5 equals 0, x plus 1 equals 0, and x minus 4 equals 0, we get x equals 5, x equals -1, and x equals 4. And what are these called again? Solutions, or just answers. Okay? So what I want to show you today is something that some people get mad at me about, and I mean, I don't care. That's how I live my life with students mad at me, right? Okay? If I put this into a calculator, that equation. Now, somebody said earlier to me that this is not right because it doesn't equal 0, because this one equals 0. How would you explain that? How would you talk to them about that?
Y equals 0.
Yeah, y equals 0. Right here when I'm graphing it, doesn't it? So I don't have equals 0, I have equals y. Or in this case, because our calculator's in function notation, it equals f of x. Okay? So what I want you to notice by looking at the calculator is that this graph crosses the x-axis at -1, 4, and 5. So that's why a lot of people are mad, because that took me like 3 seconds to do, and this took me, I don't know, 12 or maybe 16. Okay? So, but this is another way we can, another avenue that we can go when we're solving polynomial equations. But today we want to get a little bit more specific about the graph. Okay? When I'm looking at this graph, first of all, we need to pretend that it's not there for just a second. And we just need to look at the actual problem from the very beginning. Okay? There's a couple things that we need to talk about as far as vocabulary-wise. Degree. You've heard this word before in lots of different situations. It's one of those math words that have a lot of different meanings in different situations. I think earlier mathematicians just got bored making up new words, so they just used the same word for lots of different things. Okay? In this case, what we're talking about when we say degree, we're talking about the highest exponent. Okay? So if you're looking at the degree of this problem, make it a little easier on myself. There. If we're looking at the degree of this problem, what is the degree of this problem? 3. The degree is 3, because that's what the highest exponent is. Okay? We also need to talk about the number of turns this particular graph has. Now, later on, you're going to be able to tell me how many turns it is without looking at the graph, but let's pretend we can see the graph for just a second. Now, you can't see where it goes up here, but we can assume that it comes back down at some point, right? How many turns does it have? How many changes of directions does this graph have? Two turns, okay? If we know the degree, is there any way we can figure out the number of turns? It's one less. Okay? Now, this is the most number of turns it'll have. Okay? I'm going to leave that for just a second because we can't really see it in this example. I'll be able to show you another example here in a second where it doesn't quite make sense, but in our conversation, I think it'll make sense. So we're just going to leave it for now. Okay? The other thing that we need to talk about is its behavior. Specifically, its end behavior. Not behavior, end behavior. Okay? There's two directions. We're going to talk about it in two ways. Okay? The English way and the math way. Okay? So the English way we're going to talk about is to the left and to the right. That's what we would say in English, right? How is this graph behaving to the left? Ugh. Well, how would we say that the math way? Well, we're talking about just specifically to the left. So we're saying as x goes to where? Where's it going to the left? How do we say to the left in math? Negative infinity. As x is going to negative infinity, what is it doing? It's falling. It falls. Okay? As x is going to negative infinity, it falls. How would we say it, if we're talking about to the right, how would we say that in math? As x goes to infinity. What's happening in this particular graph? It rises, okay? Whoops. Rises, okay? So is there a way, like I just had the graph up here and we looked at it, but is there a way for us to figure any of this stuff out without even looking at the graph at all? Oh yeah, we think about it, right? Okay? We know the degree. We can look at that. We can figure out the maximum number of turns, which is one less than the degree, right? In this case, 2. Okay? Now, look at the leading coefficient. There's another good vocabulary word for you. Leading coefficient. What do you think leading coefficient means? The first one, almost. It's the first one if the equation is in standard form. Yeah. What do I mean by standard form? The highest exponent, and then the next highest exponent, and then the next highest exponent, and so on until we get to the constant. Does that make sense? So the leading coefficient in this problem is positive or negative? It's positive. Wait, what happens to the right? It rises? Could those two things have anything to do with each other? Okay, the answer is yes. If the leading coefficient is positive, it rises to the right. So if it rises to the right, and I know it has the most 2 turns, 1, 2, what's happening to the left? Wow. Dun, dun, dun. Let's do another one so you can see that I'm telling the truth. y equals x to the 5th minus 3x to the 3rd plus 2. So the first thing we want to identify is the degree. What's the degree? 5. Degree is the highest exponent. Okay? Now, how many turns will it have maximum? 4. 4 turns. Then we want the end behavior. To the left and to the right. Well, the degree, well, let's see, what's the leading coefficient? Can we just write, abbreviate it LC? Are you okay with that? My LC is what?
2.
Positive. What is the leading coefficient, by the way? 1. It's the first coefficient because these are in order, aren't they? Okay? So my leading coefficient is positive, so we know it rises to the right. How many turns is it going to have? At least, at most 4, right? 1, 2, 3, 4. 1, 2, 3, 4 turns. So what's happening to the right? We said it rises. What's happening to the left? Falls. Now let's go see how close we are. Please stop telling me that. Stop telling me that. Stop telling me that. X raised to the 5th minus 3x raised to the 3rd plus 2. Does it rise, does it rise to the right? Does it fall to the left?
Yes.
Does it have 4 turns? I only see 2. I see 1 right here, and I see 1 right here. This one's just kind of going over. It's not really changing direction. It's still rising, isn't it? God bless you. Not this time. There might be, but it's too small for us to tell. So for now, we're just going to say that there's 2. Okay? Now we know it's maximum of 4, right? Could it be 3?
No.
If it's 3, our end behavior is going to be the same. No. So if our degree is 5, we would have 4 turns or 2 turns. Or 0?
Yes.
Okay. What if my degree was 8? I would have maximum of 7 or 5 or 3 or 1. So if my turns is not exactly what I think it is, like 1 less than the degree, how many is it going to change by? By 2, right? It's going to decrease by 2 because of the fact that our end behavior is going to be correct. Okay? Our leading coefficient tells me my behavior to the right. It's positive, so it rises. Most 4 turns, my left behavior has to fall. Okay? Does that make sense? Do you have any questions about that? So the only other thing that you're going to need to do for your homework is to graph this. Okay? I'm going to give you some graph paper. You don't even have to graph it. You don't even have to draw it yourself. Okay? You know what your graph looks like. I'd like you to try to do this before you do your graph, like I just showed you. Just kind of check yourself with the graph. Okay? But when you go to draw the graph, I don't want this. That's pretty close, isn't it?
Yeah.
Does it cross the x-axis where it says on the graph it does? I would like those to be correct. You're going to have all of your tick marks on your graph paper, right? Your graph paper is going to be specific. You're going to have all your tick marks on your graph. I would like you to make sure that it crosses on the x-axis and the y-axis where it says it does on your graph. Other than that, I'm not going to be too picky, even though I could, because you could easily go Control-T, right? Control-T to a table and get all sorts of points that it passes through, couldn't you? Okay? I'm not going to make you do that. I just want you to give me a little bit of specifics as far as where it crosses on the x-axis and If perchance it crosses the y-axis, make sure those are correct. Fair enough? Any questions about this?